Okay, let's discuss one of the very common uh, challenges uh, in the distributed data storage. So whenever we are designing system where we are due to the high volume of data and also want to meet the low latency uh, non-functional requirements, so meet the our system is so real times uh, with the in terms of the application performance. So we are going to distribute our data into the different data centers. So this is the one of the approach where uh, we are able to allow our customer can access the data as the nearest, so that our system latency is low. That means if one person particular regions here they are trying to access data, if data are the only these places, it will take a larger latency. So the overall objective of the system design is that we can make our system as real-time response. And this is the feasible through low latency. Low latency means the location from where customers trying to access data, the nearest data center will serve the request. So for those scenarios, we are going to store the data in the distributed system. Okay, distributed system, so that key the customer from the nearest location can access data and we can meet the real times performance deliver the performance system to the customer. So this is good design, and we have to allow anywhere across the geolocation customer can access my application. Okay, let's say here one application requested X data. The X data are quickly response. Let's assume this is also customer. They have requested I want to X data. So they need the X data here as well as. So this is the only challenge is we have to keep the same data in the different data center as well as. That means if let's see this X data are someone going to the change and modify it's become a Y. So question is that if this customer trying to get access the same data, it is getting access X or Y. If the customer getting the data X, that means the our system is very reliable and system maintain the data state as a consistently or not. If system get X, that means our system is not reliable. Our data is not consistent because here data is updated by Y, here data should be the Y. So this is the challenges about the data consistency when we are storing the same data in the duplicate different data center or different server. So there are lots of techniques available through which we can provide the consistency. But providing the consistency, we have some trade-off as well. If we are providing very strong consistency, then we have to lose some feature like availability or maybe your low latency. So if you want to maintain the low latency, real time, very high performance system, that's very hard to meet the strong consistency. So we as a system design engineer, our responsibility, we have to be carefully understand the trade-off these concepts. Customer want consistency, customer want low latency, customer want performance system, customer want highly available system. Customer can ask everything. But what, as a system design engineer, what the feasible solution for the customer we have to offer? So, in the distributed data set, how we are make data consistent. So today we are going to talk the one of the basics of the data consistency. One is a very strong consistency, and one is the eventual consistency. So this terminology, while you discussing with the architect or discussing with the junior, discussing with the tech lead, many here architects say here let's we decide we are going to the to eventual consistency. So what the meaning of eventual consistency? We have must know so that we can design them, we can understand them. So consistency is clear. That means the data, whatever the data have, the same data is available for everywhere, for everyone across the geographical location. That is consistency means your data is always correct, accurate, and available to everyone. That is means consistency. But what is the eventual consistency? We are going to talk. These are the nowadays in the very big ecosystems where you want your application can be available 24 multiplied by 7 across the geographical locations and highly available system you want to maintain the low latency, then we have to compromise just about the consistency some fractions of a time. So lots of domains, industries, use cases where you cannot compromise consistency. But some places, some applications can be compromised little bit about the consistency. And on the behalf of those, we can offer to the customer very high performance, highly available, and low latency system to the customer. So we have to be carefully understand the trade-off between these the system design concepts. So let's talk about the eventual consistency. So what do we mean by eventual consistency? So you can say it is a consistency model used to in the distributed system to ensure that data is eventually consistent across the all the node in the system, even if they are not immediately consistent. What do you mean that? That means in the distributed data center, we have a store data in the different data center. Okay, okay, right. Let's say this data are available, and if the customer are modify this data available here, so this will going to replicate, going to update in every the available node. So while updating everyone in the data center might be take some time. So let's this data are going to updated here, but customer are trying to access from this location. So they are getting the old data for some period of time. So if is it okay for the business for the use case where we can go eventual consistency. Maybe after fraction of times, because our systems are going to replicate all the updated content in the every places. So those fractions of times, if our customer is ready or our business domain is ready, then this consistency model we can propose a consistency model. That means the data will going to consistent means they are going to sync every node in the distributed system, but not immediately just now, but little bit delay. That is known as a eventual consistency. This model say we are guarantee we are going to consistency your data in the every distributed node, but not now, just not immediately when the request comes. So it is the compromise, the consistency and the availability, where the system prioritize the availability and the accept temporarily inconsistency. So this is a trade-off. So we have to be carefully articulate this concept with the client. The really client want the consistency, strong consistency model, then we have to not meet the low latency, high performant, highly available systems. Okay, so but this model say many use cases, many applications, little bit delay happen, no problem. That is the nature of the business, right? We're going to talk the use cases as well. But the eventual consistency model say we are going to sync data, consistent data across the distributed all the node somehow, but not now, not immediately, but little bit delay. So these are some basic concept in the eventual consistency. So we have to first understand the meaning of consistency. Consistency meaning that's the whatever the data you have. Let's we have a one data set data X, and we have another data center they have data also X, and we have another data center data also have X. Okay. Why we are keeping this data in the multiple places? Because we want data served across the geolocation with a low latency. That means the nearest customer can get data from the nearest data center. So objective is that we as a system design engineer, our objective we have to deliver very highly performant system to the customer with a low latency. But the challenge is whatever the data we are storing might be need to require to update. So here let's data is going to modify by the different nature. So question is that this data must be available here. This data must be available here as well, right? That means currently this data is not consistent state. Here is a let's see Y data. Here is the X data. Consistency means this is also must be same. This is also must be same. If now our data is consistent, so this eventual consistency say we are guarantee them we are going to make your data consistent. That means ki across all the node you are getting the same data, but not the immediately. Let's see here request update happen the same time. I'm not going to sync. I'm not going to update. But this is the your eventual consistency. Means after fractions of delay, this data going to update, this data going to update. Not the same thread, not the same request, but the different requests, different threads, different times. Maybe lots of approach we are going to talk. How to sync data, how to make data consistent across the multiple nodes. So consistency means availability means the system is able to respond or request data even data is not consistent. Here say here let's data is not modified, still data is available to read here. Maybe not consistent, system is not consistent, but system is always available. What happened? You can say now if I am going to get any update, we have to block all the table. Let maybe apply the lock. I am not going to allow anyone until I am not going to sync them. So somewhere if you want to stop the accessing to other system until you are not able to sync, means you are compromising your availability. This data some period of times while syncing happening, you are not allowed customer can access. So this is a scenario we have to compromise somehow availability, but availability say no problem. Whatever the data we have, we are available to serve the request. And is a partition tolerance. System can continue to function even their network partition happen. What happens because these are the distributed nodes, they are connected to each other, they are sending data. Might be some network failure happen, cable failure happen, some bandwidth problem happen, something. So if something failure also happen, your data might be not synced. Let's happen this data center sync, but this sync failure happen. What happened? You are allowing the this data center customer can read data or not. So there is a partition tolerance. Means if something happen between the data center syncing happen, what the system should be behind. So all these things consider come under eventual consistency. So eventual consistency say our if we are designing eventual consistency, we are guarantee that the node is going to be become consistent, but not necessarily now. Because if any fault happen, if any restart happen, something happen, still we can maintain the all the changes available here in the maybe event source database, and we are going to the sync whenever data is available, when networks connection established, when bandwidth clear happen, but data is guaranteed they are going to the sync, but it will take some time, not immediately. This is just one conditional, you can say, eventual consistency. Eventual consistency is really very good idea where we are delivering system with a low latency and high performance available system with a consistent model, as well as just eventual consistency, not immediately but later sometimes. Let's talk about the architectures of the eventual systems. So first, the distributed data store. That means must we are going to apply this architecture where our data are stored in the multiples data center, right? And this architecture ensure that whatever the data we are receiving here, that must be updated every node. Every node must have the updated, consistent, accurate data. So that is happen through syncing, replication. Means data is replicated across the multiple node to ensure the availability. Whatever data here available, I can replicate the same data, copy the same data in the here also, here also, here also, here also, so that the data is available. And this architecture is a distributed data node and your replication strategy. And also we have to resolve some conflict resolution, because mechanisms we are putting something conflict happen with the help of concurrent update. If because our system is highly available, multiple requests come simultaneously, some data concurrently going to update by the two times, some update, some delete, some update. Then we have to ensure that if some data conflict happened between the distributed node, we are ensure that conflict resolution module to conflict resolve all the data inconsistency issue, ensure that data is consistent across all the data set. Generally, this activity about the replication, conflict resolve, syncing happen as a background service. This may be lots of strategy we're going to talk: periodic syncing data, background service, event sourcing, messaging queue. Lots of approach here available through which we are going to replicate data from the one distributed node to the multiple distributed nodes. Okay, so these are the basic architecture where all the data center, replication module that replicate data, conflict resolution module that resolve the conflict, and all these activities happen as a background process. So lots of approach. I'm not going to cover each and every approaches, but lots of approach available through which we are ensuring that our data, accurate data, correct data is available all the distributed node or data centers. There are lots of approaches, but little bit like maybe last right win, multi-version concurrency control, conflict-free replicated data types, read repair, backgrounds synchronizations. So lots of approach. Each engineering teams have multiple use cases, multiple scenario where multiple way, multiple techniques available through which our objective is that we are going to guarantee our customer all the distributed net which we have, whatever the data is correct data available, that data is available to the every node. This is the overall objective. This replica, how to do, maybe one approach, you the node which receive the right data, they can responsibly going to update here, going to update here, going to update here, going to update happen. This is the one way. But let's assume this our distributed node have a 100 nodes. So it will going to do all the concept synchronously or asynchronously, or maybe some other service are going to see. So lots of approach available where the right the main server which receive the right operation, they are going to sync to other. Yeah, just say they sync to the one and other responsibility sync other responsibility sync other responsibility sync to other. Or maybe, hey, we have some different event sourcing or some queue, I am going to the put data in the queue, this queue, and each and everyone going to, I just subscribe this queue, hey, something happened, I read the update data, I read the update data, I read the update data, I read the update data. So lots of approach available. Hey, we are going to the apply some queue mechanic, or maybe some sync server. Hey, I am just writing to the one sync server is responsible to read data from the queue and start multiple threads, and each thread going to sync data. So pull mechanism, push mechanism. So lots of mechanism approaches available through which you are going to ensuring that anyhow our data are going to available across all the data centers nodes. So this is the one approach is that last right win. So most recent update is considered the correct versions, and user update data, their profile information. Latest update is considered a correct version. Simple update such as user profile or caching something. So something say, hey, one update happened, two update happened, three update. So but the last update would be the correct data that go to be the sync everywhere. Might be. So might be scenario where users today update period of times updated his address. After some time again, his address is a mobile number. After some period again, three equal update happen. So whenever syncing happen between the different nodes, this approach say what are the last update happen here. This correct state just sync those only, not update first this, then this, then this, then this. The multiple approaches. You can say every sync, every update going to update everywhere. Something, hey, what are the final update? Final update to sync to everywhere. Final state is the current state. Okay, so these are the maybe sometime the multi-version concurrency control. Yes, that means multiple version of data store and conflicts are resolved based on the version. So might be concurrent users are updating data and we apply the multiple versioning. So we have to properly maybe user update a particular document, our system install the multiple version of document and resolve conflict based on the version number. So collaborating editing, yeah, versioning control systems, where such kind of a ensuring that our uh, data, our code, our final versions will be available. Sometimes you can say conflict-free replicated data types as well. So data structures that are designed to ensure that the data is updated always valid and can be merged without conflict. So distributed counters that increments the independently on the multiple nodes, and system ensure that the counter value are eventually consistent. Generally distributed counter caching, leaderboard, lots of approaches available where you can say conflict to replicate and data storage. Sometimes the read repair, that means a system read data from the multiple nodes and repair any inconsistency. So there is some concept. Hey, figure out. Hey, these are the lots of components where the data inconsistency. This is the node have a data inconsistency. Let's sync and correct it. So, example, system read data from the multiple nodes and repair any inconsistency by updating the inconsistent node with the correct value. Maybe data caching, CDNs, all the CDNs generally have their own copy. So they are just checking, reading to the main server. Hey, main server have any change? Let's update ourselves. So lots of approaches where we are going to apply many we are times we are writing the background synchronized periodic job task queue pull mechanism post mechanism, and we have to ensure that data is synchronized between the nodes maybe every hour, every minute, or every one batch full, or maybe some data where lots of places where our data volume is very high. Those scenario always we go the periodic time basis, maybe every 5 minutes, every 2 minutes we are going to sync data in everywhere. So these are lots of techniques, so we're not going to discuss everything, but you have to just go and find out lots of approaches technique available for the synchronous syncing, asynchronous syncing, as well as replication, as well as the objective is that we are guarantee our customer, hey, your data always be consistent whenever you are going to any change, but little bit delay. After some time, we are our system is not going to lost any data in anyhow. Okay, so for those scenario, many places you are applying the queuing system, message system, event sourcing. They are able to ensure that the data is properly tracked. Even the fault tolerant happen, even some data failure happen. We have already stored data in the particular messaging queue, event store database, and from the event store you can read data and replay. And we are confirming customer, hey, your data is always available in the case of fault tolerant, in the case of network failure, in the case of something happen. But if you send data, we receive. Our responsibility, we have to ensure that data is going to sync, going to consistent across all the node after period of times. So if we are properly designs our eventual consistency, so we can commit to the customer, hey, we are going to design system that is highly available. System remain available even the maybe network failure happen, maybe node failure happen, maybe data inconsistency, but system always be available. And in this way, we can improve the performance because we are replicating, we are handling data large, but they are distributed across the nearest customer locations. The system can be handled high read and high write and scale data horizontally because we are going to scale data, and as closest nearest to the customer, we are putting data and the data replication happen. So our system, our customer, our clients can get very high quick response because we are going horizontal scaling is the one of the key parameters is they are going to make the low latency means we are going to response customer as a real time response, and we have to also ensure simplify the conflict resolution mechanism. So we have to ensure that our system is highly available, lots of concurrent happen, so we are ensure that this strategy like eventual consistency ensure that your data conflicts are resolved, always data available, customer and rely the systems. While doing the consistency, we have to ensure be carefully. There are some challenges you face, while limitation you have to face about the data inconsistency. We have to properly communicate, we have to properly design, then whatever the data inconsistency happen, okay, that's only the period of times until your server is down, server is crashed, network is not properly working. During that times Might be customer face data inconsistency, but once network restore, partition restore, maybe server up happen, we have to restore data. So properly backup, restore, event restore data, replay data, all the concept we have available. On the behalf of that, we are ensuring customer, hey, don't worry, data inconsistency happen only a period of times. But after that, your data must be inconsistent. And also ensure that conflict resolution complexity, because our systems are distributed system, multiple concurrent read write happen. Solely possible some data maybe conflict happen. We have to ensure that properly implemented make our conflict resolution models. And sometimes while making consistency, eventual consistency, your latency become high. Okay, the data maybe take time to propagate across all the distributed node, leading maybe data a higher latency. Maybe so we have to somehow compromise, because the here latency means data can be reach late processing, right? So please keep in the mind while designing system that are very highly available, and you are going to propose the eventual consistency. So for eventual consistency, as a engineering teams, we are not more worried. We are lots of tools and technology available that help us this. We have to just select right technology tools we have. Let's say Apache Cassandra is available for us. This, these are the NoSQL database designed for the eventual consistency. They have a lots of clusters of nodes. Each nodes are responsible to make data eventually consistent across the geographical clusters of the data set. Even you can go to the cloud provider. Amazon DynamoDB is fully managed SQL database that support the eventual consistency. So lots of Riak is a distributed data store support the eventual consistency. Even you can go with the Apache Kafka for the messaging systems that support eventual consistency. So you can say just this is the concept we should aware. In this way, we can offer the high performance system to the customer. So while the implementation, we have to not so worry, because the lots of technology tools available that's already implemented this eventual consistent replication, eventual consistent conflict resolution, all the things, whatever the architecture concept we learn study, don't worry, that's already taken care by the your data centers, whatever the data storage software you are applying. Okay, so while system designing, we should aware the available technology for the particular concepts. And these things already lots of industries are using. Let's go all Amazon shopping cart. Amazon shopping cart system are eventual consistency to ensure that highly available. Notice the Amazons are accessed by the data in the different region, different location across the world. So let's say particular list of product, list of product, list of product. So list of product here, list of product. So each customer saying, hey, what is the list of product for the particular mobile? So let's set a product list you can view. So here views, here view, and different location view. That's good. But let's one vendors are going to add one more product in the particular category. So at the same time, might be the particular instances, every locations, every data center might be not available those new product. Okay, so those scenario a little bit delay, and after that they are going to the sync every data center. And now after some period of times, every users across the geographical locations data is available. So this shopping carts also implemented as a eventual consistent. Similarly, your Google search engine also use the build the search indexing is the built using the distributed uh, system and employ here the eventual consistency while the maintaining the search indexes. Twitter timelines built using the distributed system that use the eventual consistencies that ensure that system is highly available and scalable. So lots of scenario where like online particular event happen, maybe some social media. Here, lots of volumes of data is going to serve. You want your system should be highly available. Little bit consistency delay happen, no problem. That can be managed. Let's take one customers, very popular customers. They have millions of followers. They are going to uploading one post or one particular photo. This photo might be while update same time every millions of follower cannot get the updated value. But after fractions of time, little bit times, little bit DAGs, our technology sync the data in the across the data center, and then after that, everyone can available. So social media platforms, internet platform, online sub maybe some live broadcasting, some packets, some messages are undelivered. Not a problem. It's manageable, right? So, but some places different technology, lots of tools and technology available to meet this kind of a high volume of data with the high consistency, eventual consistency. So it's consistency, a data model have a multiple approaches: strong consistency, eventual consistency, period times consistency, or not consistency. The some system might be some fraction of data lost, no problem, man. But some systems say data lost is not compromised. Delay can be compromised, right? So depend upon the customer use case, data situation, where you are ensured that our data lost is not compromised. Data consistency must required, maybe but not strong consistency, but eventual consistency we can offer. And in this offering eventual consistency, we can get lots of other benefit: low latency, high availability, fault tolerance, fault management, scalability. So these key feature we can get from this eventual consistency. So while the system designing, please be aware these concepts. These lots of help. We know the concept, we know the technique, and also our responsibility. We have to aware the market available technology tool set available so that you can select right technology, right tool to meet your system designs. Hope this information is helpful for you. Thank you.